So now we're moving into chapter 3. In this textbook, it's entitled One-Dimensional Steady-State Conduction. Each of these phrases means something. So one-dimensional, so it's not multi, it's just one dimension. We're going to be able to handle it in the rectangular system. That'll be the whole section 3.1, just temperature is a function of x, like a Cartesian coordinate system, rectangular coordinate system, okay. As well as in radial systems. So temperature is a function of r in the cylindrical as well as r in the spherical coordinate system. That's what we mean by one-dimensional. And then steady state, so it's not a function of time, it's steady state conduction. So this is really where it becomes more mechanical engineering, more applied. We take that heavily mathematical information out of chapter 2, and then we solve some problems and solve them very efficiently. So let's continue on. So coming out of chapter 2, these were some of the key equations, heat diffusion equation. So in the rectangular coordinate system, if it's steady state, what happens to that transient term? And if it's one-dimensional, we don't have z and y, we just have this as the surviving term. You could have q dot, or you could not have q dot. Remind me, what is q dot? Heat generation. Heat generation. Similarly, in the cylindrical, basically r is the key dimension or parameter. We're solving for temperature as a function of the radial dimension r in cylindrical and a steady state, as well as in the spherical steady state. So these are the surviving terms for the second derivative of the temperature profile. This is basically the Laplacian of the temperature profile. Okay. So let's solve this problem. We have a wall of thickness L. So we'll go ahead and introduce, we've done this before, coordinate system starting at x equal to 0 and going to x equal to L. And there's our wall. It has a thermal conductivity K. And it's a specified temperature T1 at x equal to 0 and T2 at x equal to L. A lot of times they'll put a temperature scale here, and maybe we'll indicate right there that that's temperature T1 at x equal to 0. And this is temperature T2, indicating different temperature at the second at x equal to L. First part, solve for the temperature distribution in the wall. So we're asked to find T as a function of x. How do we do that? Get the differential equation, the heat diffusion equation for this problem. Is there any q dot in this problem? No, there's no q dot. So the equation boils down to, let me write it this way, derivative with respect to space, the thermal conductivity, the derivative of temperature with respect to space, equal to 0. Can I take that thermal conductivity outside of the derivative? Yeah, because there's nothing to indicate it's a function of space or a function of temperature. It's just a constant. That's often the assumption. And so you could just write it like that. Now, we need two boundary conditions, boundary condition number 1 and boundary condition number 2, to have a nice mathematical problem. Then we forget that we're an engineer and we pretend we're a mathematician and we solve it. So let's do that. What is our boundary condition number 1? And the temperature at L is equal to T2. Those are our two boundary conditions. In the classification of boundary conditions, it's specified temperature at both of them, not insulated or symmetrical or specified heat flux or a convective boundary condition. This is the boundary condition we love. So the strategy is separate and integrate. So the first separation, you put the D, well, first of all, you could take, and let me do this, equal to 0, then I'm going to have dx over k. You see the mathematical little change that I did? I separated. So I put dx over on the other side as well as k. But they both multiply 0. So guess what's on the right-hand side? 0. It's 0. Okay? It's not like they just evaporated, but I moved them separating to the other side. So now I integrate. When I integrate, we get that dt dx is equal to our first constant of integration. Let's do separate again. dt is equal to c1 dx. Let's integrate. So we get that t is equal to c1x plus c2, our second constant of integration. Does this look familiar? Yes, please. Nod head up and down. Yes. Okay, thank you. Then we continue on, and we say apply boundary condition number 1, and we get that T1, that's the temperature evaluated at x equal to 0, is equal to C1 times 0 plus C2. Can I solve for one of those constants right away? Sure. I conclude that C2 is equal to T1. Let's go to the second boundary condition. And we find that T2 is equal to C1 x equal to L plus C2. Well, you could put in T1 right away because you already solved for C2, right? And now I can solve for C1. C1 is equal to T2 minus T1 divided by L. Thumbs up if you agree. Good. Very good. So let's put them together. So we find that temperature is a general function of x is equal to my constant C1, T2 minus T1 divided by L, times x plus my constant C2, which is T1. And there it is. So this is the answer for part A. Isn't that what we were asked to find? The next part, the heat flux in the wall. The heat flux in the wall. What symbol, I know this is a review, but it was a long, 3 or 4 day weekend that we just had? It was a great weekend, right? I had fun. Hope you did too. But what are we asked to solve for? What symbol do you want to use for the answer for part? We want to use Q double prime. Isn't that our heat flux? How do we calculate it? Whose law? Fourier's law. That's right. So it's minus K and then the derivative of temperature with respect to X. Is that the correct application? Do I need the minus sign? Yeah. And what about the derivative? There's 2 ways to calculate this derivative. Let me just say it's 2 ways. One is use the temperature as a function of X and just do the derivative, the calculation of dt dx. Go back to this equation in the red box and differentiate it. There's another way to do it. That's to say, right over here, I found that dt dx was equal to C1. And you know, I already found C1. It's right here. It's T2 minus T1 divided by L. Professor, you seem to be going in circles. This will pay off when we get to the 2 radial systems, the cylindrical and the spherical. When you get to cylindrical and spherical, remember right here that I can do dt dx by going back and looking for, hey, I already solved for that. It's equal to C1, blah, blah, blah. Okay? All right. Right now, it's not much difference in effort. But what is then Q double prime? It's equal to negative K times dt dx, which is T2 minus T1 divided by L. True? Are we ready for a clicker question? I think I have a clicker question ready for you. So this is just helping you warm up a little bit. I think it's on the next slide. I hope it is. As this is shown right here in this sketch, as I've shown it, T1 minus T2, is that either negative, answer A, equal to 0, answer B, or is it positive, answer C? I don't know why that does that. Is everybody in? I'm going to shut it down, okay? All right, let's stop. Now, this, I tried to emphasize that this is the temperature's axis, right? And so kind of low temperature to increasing temperature up to the highest temperature. So this height is a indication of its temperature value, true? I know I'm making this almost too easy, but when we get to cylindrical, spherical, sometimes these little reminders help, okay? So guess what? T2 is coming in at this value right here, and T1 is coming in at that value, which is a higher temperature. T1. T1 is greater than T2. So I would expect T1 minus a smaller value is, but we never get 100%, do we? But you'll see that there's easy to be off by a negative sign, and I've just done this enough that when you try and do it on your own, I'm trying to help you. This is a slippery spot. Danger here. Slow down. Got it? All right. Let's jump back. Because right now, I'm looking at this equation, and I don't like that minus sign. So where can I slip that minus sign? K over L times T1 minus T2. True? And T1 minus T2, if I'm thinking of the flow from left to right, if I'm thinking of heat transfer in this direction, doesn't T1 need to be greater than T2? Yeah. So anyway, the answer for part B, the heat flux, is equal to K over L T1 minus T2. If you want to put an X on it, that's great, that's fine, but we already know it's only one-dimensional. You can leave the X off. Part C. This is a tough question. What is the rate of heat transfer through the wall? What have I encouraged you to do? To think about what symbol I would like to use for that answer. And so I'm going to ask a clicker question. Answer A, B, or C. These are your three choices. The answer for part C, the symbol I'd like to use would be Q double prime, or Q dot, or Q. And I'm only going to give 30 seconds. Is everybody in? Everybody in? Let's go ahead and stop. Q double prime was our answer for part B, so I think we can rule that one out. It's not the heat flux, it's the rate of heat transfer. How do I calculate the rate of heat transfer? I have the heat flux and I multiply by the area, do I not? And so some people would put the dot on top, thinking, hey, this is a rate. Dot on top means rate. But in this class, what does the dot on top of the Q mean? All right, let's go ahead and grade it. This is the correct answer, true. So now that we know what we're asked to solve for, we just take and do it. And so this Q is equal to Ka divided by L times T1 minus T2. Part D, calculate the thermal resistance of this wall. What we need to do is I'm going to jump to another slide, and then I'm going to talk about an analogy. An analogy between something that you're hopefully very familiar with, and that's electrical circuits where there's a resistor in it. You have two nodes and you put in something like this in it. It's electrical. That's a resistor. Okay? What flows through the resistor? Current. Current is what flows through the resistor. Okay, what symbol are you familiar with that you used for current? And then what is a typical SI unit for current? Both the symbol and the SI unit. I is the symbol and the unit? Ampere. So I like to put a bracket, say, hey, I'm talking about an ampere, not a letter A or material A or area or something like that. This is an ampere, right? So what other characteristic of the resistor, it characterizes its resistance. And then what drives the flow through the resistor. So I'm now talk about two more things. We already talked about what went through it, current. What resists the flow of current through it? It's its resistance. What symbol do you use for resistance? And what is your favorite SI unit for resistance? R for the symbol, and it's in ohms. True? Isn't that the symbol for ohm? All right. What drives the current through the resistor characterized by so many ohms? What drives it through? Voltage difference. So what drives it is the flow is an EMF. Anybody familiar with that term? Electromotive force, or something like that. Now, what symbol do you like to put for voltage? V. And what SI unit? Volt. And that always is a little tricky. So instead of V, some people have put E. Why E? Electromotive force, E for voltage. Now we test your skills a little bit. You have over here ground. Okay, and we take and we put a voltmeter, and right here we measure that this electromotive force, with the voltage at that point, is 10 volts DC. You know, it's all just easy DC. And this is my second location. E2 is 10 volts. What is the flow of current through this resistor? 0. Somebody says, not enough volts. Okay, make it 100 volts and 100 volts. It's still 0. You have to have a voltage difference, a voltage change between the two ends of the resistor. I heard that earlier, but when you write Ohm's law, how many people can write Ohm's law? Oh yeah, right off, I got it, back of my hand. It's in my memory forever. Ohm's law is easy. You got it, right? Can you write Ohm's law from memory? Go ahead and write it down. I'm going to pause. All right, so the overwhelming consensus is V equal to IR. But if somebody says it's the voltage difference, not just 1 volt, so I would try to encourage you to put delta V in there. And because V is the measure of the volts as a SI unit, and you like to not have the same thing, I would put a delta E. Does that make sense? So I change it a little bit. Change in the voltage across the resistor. So you can rewrite this equation as I equals delta E over R. What is I again? It's a flow. It's something flowing through. What is delta E? It's the driving difference in the potential. What is R? Resistance. So now we look over here at our slab problem, and we had T1 on one side, T2 on the other, and we had that the flow of heat Q was equal to T1 minus T2 divided by L over Ka. And all you do is look and you do a little name calling, and you identify a thermal, not electrical, but a thermal resistance for a slab, L over Ka. Because what flows? Heat is what's flowing. What drives it? A difference of potential, but this potential is the temperature. A difference in temperature, not voltage, a difference in temperature. But that drives the flow. What resists it? Thermal resistance. So now you can look at this and you can say, if I increase the thickness of the slab, if L goes up, what does the thermal resistance do? Goes up. That makes sense. If I add more insulation, I cut down on the heat transfer. If the area goes up, what does the thermal resistance do? And then the next one, if I increase the thermal conductivity, what does the resistance do? Thermal resistance goes down. So this is almost too easy. You're saying, man, give us something challenging today. Just remember L over Ka, L over Ka, L over Ka. It's a resistor. We use that a lot in modeling thermal networks. heat transfer. So we come back to this problem, and we finish it out, and that thermal resistance to the wall, R thermal, is L over Ka. All right. We can get a thermal resistance for convection as well. We can get a convection resistance. They did this in chapter 1. I skipped it. Now it's the proper time to bring it in. So if I have a slab, and then over here I have a fluid, and that fluid is characterized by a temperature of the fluid and a convection coefficient, I can go back and I can say, what is the rate of heat transfer, Q, from the solid? The solid's at a temperature T. Let's call this temperature T1 and this temperature T2. It really, you should be able to write it for whatever temperature appropriate. So T2 is, for this problem, the temperature of the surface of the solid exposed to the fluid. That convective heat transfer, given by somebody's rate equation, Newton's law of cooling, is the convection coefficient, the area, times T2 minus T infinity. Or you could write it T2 minus T infinity divided by 1 over HA. And so the resistance thermal convection is 1 over HA. As the convection coefficient goes up, resistance to heat transfer goes down. Area goes up, the resistance goes down. So we could put a little network here and have 3 nodes. The nodes, they have, just like voltage was for electric network, we have temperature at each of our nodes in a thermal network. So we're going to have T1 at that node, T2 at that node, and T infinity out here. And what do we have? We could have flow of heat through that slab. That slab has a resistance thermal, L over Ka, as well as the resistance to heat transfer coming off the surface and getting into the fluid. That resistance thermal is equal to 1 over HA. So you could put resistors in series. Aren't these 2 resistors in series? Yeah. You betcha. Absolutely. You can sum the 2 resistances, etc. Yes?
Yeah, the influx of
Oh, this is wrong. Sorry. That's right. I put the area in there. Thank you for fixing that. Is it good now? All right. The convective thermal resistance, clicker question, is equal to, right here, 1 over HA. I tried to type it, right? Just what we just had. 1 over HA. What are the typical SI units for that R? What are the typical SI units? Watts per meter squared per watt. This is meter squared degree C per watt, degree C per watt, or watt per degree C. Everybody in? Well, there's 2 ways to do this. I'm sure some people are very confident they got the right answer. They said this R, this is what I'm asking, is 1 over HA. I can recall from memory what the area units, typical SI units on area are. Meters squared, right? And then convection coefficient. And so these cancel, answers that. Another one is you could say, look, we said that Q is equal to a change in temperature divided by some resistance, true? So the resistance is equal to the change in temperature divided by Q. What are the typical units for the change in temperature? What are the units for the flow? You get the same answer, degree C per watt. So which one is correct? D. All right, let's press forward. So we can put thermal resistors in series. Think about a wall made up of this material A, followed by this material B, followed by this material C. We can think of temperatures at unique locations, often at the interfaces, T1 at this location, T2 at this location, T3 at this location, T4 at that location, but you're not restricted. I mean, somebody says, I want the temperature in the middle of C. Fine. Put a node there and call it T5. You could put it anywhere, but it's common to put it at interfaces. All right. And we're interested, maybe we have one-dimensional heat transfer, and so the rate of heat transfer is flowing through the system, and it's just like flowing through. It goes through one resistor. What is this resistor? L over Ka. So the thermal conductivity of material A, the thickness of material A, so you think Ka and La. And then you're going to have thermal conductivity of material B and L sub B, the thickness of B. Thermal conductivity of C and the thickness of C. And so that's how you make up these resistors. The thickness of B divided by the thermal conductivity of the B in the area that the heat's flowing through. If this is a composite wall and it's a rectangular system, typically we're not changing the area. The area is the same as it flows through. All right, let's go ahead and put it here and then here. And so what about this resistor right here and that resistor right there? Wouldn't it be L sub C divided by 2, half of the thickness divided by the thermal conductivity of C area? And this would be L sub C divided by 2 divided by K of Ca. How do I combine two resistors that are in series? R equivalent is equal to R1 plus R2, isn't it? I just add them. And you can see that if I just add those, I get that it's L sub C divided by K sub Ca. Makes sense. So two resistors in series, you can just add them. So maybe you have a convection over here. Well, you'd put another T infinity, and H characterizes, so I need another node for T infinity, and I put another resistor, 1 over HA, the convection coefficient in the area. Well, those are in series. Can you do a few in parallel? Sure. What would it look like in parallel? Well, instead of having material A here and material B there, turn it 90 degrees. So there's material A, and there's material B, and everywhere along this face is a temperature T1, and everywhere along this face is a temperature T2, and it's insulated, and theoretically you put a little material in here such that it's well insulated as well between A and B, so that there's no starting out a flow in B and then it sort of jumps across to A. I know that's in reality. That happens. But theoretically, you approximate it as perfectly insulated between the layer A and B, but the heat transfer would just be coming in from the left and going out to the right, so this would be Q through the system. So you would put a node for temperature, T1, T2, and I can flow either in the top half or bottom half, through material A or through material B. Two resistors, they're in parallel. The L sub A divided by KAA. So I have the thermal conductivity of this material A, and then the L sub A is the length of it in the direction of the heat transfer flow. And then the same thing, L sub B divided by K sub BA. I apologize. I know that I'm using A for area, then using A for, oh, that's the material A. So we're recycling right in the same equation. The A doesn't mean the same thing in the same equation, which is confusing, isn't it? But I'll just say that's consistent with the book and consistent with the vast, vast, vast majority of engineering. That's just what it is. All right? So this would be the flow in. Now, you just remember from analysis, so if I'm bringing in 50 watts, I could have 40 watts go up here and 10 watts down there. So the current, splits. True? But if the same two temperatures, maybe this is 100 degrees C and this is 20 degrees C, the same two temperatures drive the flow through material on the top, A, and the material on the bottom, B. But material A may be better conductivity, higher thermal conductivity, so more watts go through there. And material B may have lower thermal conductivity. Or you could even change it up if you did this. Here's my network, and there's material A, and there's material B. Well, what did I just change? The area of B is a lot bigger than the area for the flow through A. You can have very general networks that have resistors in series, very, very common, we like that, and resistors in parallel. You just have to think a little bit more and work it out. All right, so now think about two materials, and we bring them into contact. Here's material A, and here's material B. We bring them into contact, right? But your experience says there may be something going on at the interface because surfaces have roughness, and you took two rough surfaces, you put it together, and if I zoom in, I may find that A looks like a mountain range, and B looks like a mountain range, and they hit some spots and they leave some gaps in some other spots. So there's metal-to-metal contact between A and B, but then there's some gaps. What's in the gaps? Air. Air. Or if you're an engineer, you could insert some other material to promote the heat transfer across that gap, that contact. But you could get a resistance due to the heat transfer. So what's our equation for heat transfer? Q is equal to delta T divided by R. We're going to talk about thermal resistance due to the contact. All right, so in order to help do that, let's go ahead and introduce temperature. And let's plot it as a function of x going through this system. It really doesn't matter. It's like there's a slope here, isn't there? Isn't there a slope? And that's driving the flow of heat through the material A. And then what happens is the temperature gets right here, and then there's a jump in the temperature down. And then there's another slope in material B. They're not necessarily the same slope because they have different thermal conductivity. So the heat, the dt dx is different because of thermal conductivity. But so what happens is you have maybe a change in temperature from node 1 to 2, and then change in temperature from node 2 to 3, and a change in temperature from 3 to 4. So you model this temperature jump, or it's really, you back up and you have at the same location a little bit to the right and a little bit to the left of that interface two temperature nodes, but they're infinitesimally close together because it's so small, these little mountains with the interstitial fluid. This delta T right here, what we're talking about is T2 minus T3 in this, it's a temperature difference, that gap or contact. All right, and then we have this resistance thermal contact. Now, a lot of times they say, let's just do this per unit area. And said, oh, well, since we put double prime on that Q, we got to put double prime somewhere over here. Double prime on temperature, nah, that don't make sense. Let's put double prime here. And that's what the book does. And I'm not a fan of that. I'm not a fan of it. It's confusing notation. Why? All right. Somebody just said, I learned what Q is, and I learned what Q double prime is. Please tell me, what are the SI units for Q and Q double prime? What is for Q? Watts. Double prime. Watts per meter squared. That double prime typically indicates per unit area. One length, two lengths, two strikes up there, right? All right. So then I come over here and I just learned what R was. What is the SI unit for R? Degrees C per watt. That's exactly right. Somebody says, R double prime, tell me. I like analogies. You like analogies. I see the pattern. Here, over here is the pattern. I'm going to tell you what R prime, double prime is, right? What is it? It's going to be degrees C per watt meter squared. I'm just being honest with you. I'm just being absolutely honest. The book and a lot of engineering literature put R double prime TC. It's T is for thermal, C is for contact, R is for thermal resistance, and then that double prime shouldn't be there. All right. Because what they did was, think about it, come back here. We have Q equal to delta T divided by R. We like that. We divide this by area. Shouldn't I divide this by area? And then they just said, you know what? I'm going to rename R double prime as R times A. Can you tell what R double prime units are? If this is incorrect, if this is wrong, what is the correct units for R double prime in this textbook and a lot of engineering heat transfer literature? Degrees C meters squared per watt, and this is correct. Units for R double prime. Oh, I forgot to put the TC on this. But you understand it's the thermal resistance for contact. So this is the equation. It's confusing notation, but it's out there, not just this heat transfer textbook, but a lot of heat transfer literature. I prefer to talk about a contact conductance. A lot of other textbooks talk about a contact conductance. And that contact conductance, H of C, would have watts per meter squared degree C. Conductance is reciprocal of resistance. You would treat it just like you did with the convection. But I don't think it's really emphasized and covered in this book. So I point out that if you were using a different book, maybe there's a more logical way. But hey, we're using this book and you can deal with it. It's okay. Right? You just know. This is the way they have R double prime for the thermal contact resistance defined, and the units on that are degrees C meter squared per watt. So let's take a look at this table 3.1. So there's a part A to it, and there's a part B. Let's just focus on this part, which is part A. All right. So they're saying the thermal contact resistance for metallic interfaces under vacuum conditions. So here is that R double prime TC. You see the funny units, meter squared Kelvin per watt. They multiply by 10 to the 4 and then stick the number in. So if you want the real number, you multiply the result out of the table by 10 to the minus 4. But let's take a look. You have some stainless steel, two pieces of stainless steel put together under different contact pressures. So if I have this pressure, is that a low pressure or a high pressure compared to this pressure? So this is like a high pressure, isn't it? And this would be a relatively low pressure. You can see that the contact thermal resistance changes. Does it go up or down? Just compare the two stainless steel put together under a vacuum. Higher pressures, lower resistance. That's good. It's like those mountaintops are getting smashed together on a microscopic level. Then you take a look at maybe copper. Well, copper may be more malleable, right? Isn't that the term where if you smash it, it bends and conforms, right? So there. Somebody says, is this pretty esoteric that you're under vacuum conditions? I mean, come on, engineers, do we have to design things that operate under vacuum? Space shuttle. If they got two metals together and they bolted them, something like that, and it's out there, it's in a vacuum. Okay, so this is not ridiculous. Now let's take a look at over here. This is B. Let's continue to read. So they just have aluminum. They say it's 10 micron surface roughness, one surface roughness, and they give this pressure right here. That's that contact pressure. You ready for a clicker question? I'm looking at this pressure right here, and I want to compare it to these two pressures. So I ask this clicker question, and you only get 20 seconds. Fill in the blank. The 10 to the 5th newtons per meter squared is greater than, equal to, or less than 100 kilonewtons per meter squared. What is it? Everybody in? Let's go ahead and stop. Well, I asked that at 11 o'clock. I thought this is just to give me, hey, you're here. I asked the easy question. So, what's 100? Is that 10 to the 2? What's a kilo? Is that 10 to the 3? If I multiply 100 times a kilo, is that 10 to the 5th? Is 10 to the 5th equal to 100 kilo? Ready? You're going to be working with all these people. And it was interesting, as more discussion went, people were fleeing from C over to B, and people were fleeing from A over to B. So talking to your neighbor is worth it. So my guess is 4 people still need to find neighbors that are worth talking to, and 2 people need to find neighbors that are worth talking to. Okay? So there you go. Let's grade that. But why did I ask that question? Well, I probably would have, if I was a technical editor, say, look, why don't you put that as 100 kilonewtons so it's consistent with other numbers in the table. But anyway, what you find is, what's the trend in the interstitial fluid? If you just have air, high resistance. If you have helium or hydrogen, what's a characteristic of those two gases? High thermal conductivity of the gas, the interstitial fluid. You could put some oil or glycerin. You could put some thermal paste in there. You could do a lot of things as an engineer to promote heat transfer when you have to cross a boundary of 2 dissimilar metals or contact. Thank you for your attention.